Now let's continue our discussion in chapter 3. So now we're going to introduce our informal method called black thread method and about how to construct a real line or a straight line that fits the data. So here's how it works. First of all, we have these data points and we can put a thread down, and it can be a cable, it can be a straight line, straight edge, or anything like that. So it looks like it fits the points. And then we're going to read off the 2 points on the thread. As we explained in the last video, theoretically speaking, any 2 points will do the job. However, from a practical point of view, it might be easier to read off 2 points that are relatively further from each other. So it's easier to get an accurate reading that way. Although theoretically speaking, any 2 points will work. And then we're going to use these 2 points to compute the slope of the line. And well, we have several ways to find the y-intercept. And if one of these 2 points happens to be the y-intercept, and then we have it immediately. And otherwise, assuming that one point we rid of x1, y1, and we can use this formula b equals y1 minus mx1 to calculate b. So this is one way to do it. Of course, another way to do it is simply write down the point slope form of the line. So let me just give you this example. Suppose you have the plot of voting registration versus the turnout as follows. And the horizontal axis represents the voting registration and the vertical axis represents the turnout. Well, this point seems to be scattered everywhere, and apparently there's no single line we're passing through all these points. Afterward, that's not our goal. And instead, we try to find a line that fits the data really well. So what we're going to do is put down a thread. If you look at this part of the screen, and we're going to put down our thread that kind of fits the line. And of course, let me just draw a straight line to make it look better. And so let's say this is the thread, and you can always adjust a little bit so that it appears to fit the data. And so let's say this is the thread that we choose. And now we're going to read off 2 points from the line. So let's say one point is about right here. Let's say this is the point that we're going to read off. And you can identify the coordinates of this point as, for example, the x coordinate, or theoretically speaking, is the r coordinate is 100, 90. So this is a point. Another point you can think about is right here, approximately here. So that is let's say 30, comma. I would say this is about, let's say 12 or 13. Let's say 13. And now once you have these 2 points, we can find the slope. The slope m is calculated as the rise over run. So it's the change in y divided by change in x, or in other words, is 90 minus 13 divided by 100 minus 30. So the numerator turns out to be 77, and the denominator is 70, and this turns out to be 11 over 10, or in other words, is 1.1. Either way is fine. So this is the slope. And well, instead of calculating the y-intercept, you can also write down the point slope form of the line. Namely, you have 2 points, x1, y1, and x2, y2, and then slope is m. And the point slope form of line is y equals m times x minus x1 plus y1. So this is the point slope form. So in this specific case, we can use the slope 1.1, and the point, you can use either one of these two. They will give you exactly the same answer. So let's say use the first one. So y equals 1.1 times x minus x1, which is 100, and then plus 90. So this one turns out to be 1.1x minus 110 and plus 90, which turns out to be 1.1x minus 20. So this is the point slope form of this line. You can actually check your answer by plugging x by 100. You get a 1, which is 110, minus 20 is 90. And similarly, if you use 1.1 times 30, that's 33, minus 20 will give you 13. So this is the line y equals 1.1x minus 20. This is the line that will be the equation of this black thread line right here. Well, I just want to make a few comments. First of all, when you do this question, remember that this method is kind of informal. Namely, if you have two random students to do this question separately, maybe another student that may use different color will choose a slightly different line. Maybe another student say, hey, this red line, to my eye, will fit the data better. Well, I'm not going to argue either one is correct, right, or wrong, or better than the other, and they both will be acceptable. After all, we have not introduced an objective criteria, which line will be the best line. In chapter 11, we'll make this idea more rigorous. There will be a line, one line that will fit the data very good, very good. That's the best line. There is an objective standard. But before we do that, I would say any of those lines will be acceptable. Of course, if you construct different lines, and then your equation of the line may be slightly different. And secondly, even if for the same line, we read off the points, and of course, different students may choose to read different points, and their calculating of the slope may slightly be different, maybe slightly different because of the reading differences, and those are all considered normal. And what would not be acceptable, of course, will be some lines that does not fit the data at all. For example, if some student you give it, like a line like this, that's not acceptable. And a line like this is not acceptable, or something that's not even a line, like a curve like this is not acceptable as well. So just want to keep in mind that you want a line that roughly fits the data, a line that passes through in the middle of the data points. However, at this moment, we don't have an objective standard in determining which line is the best. Now, let's take a look at the next example. Suppose in physics we have a body falling freely from rest, and in a vacuum, or namely we don't consider the air resistance, and it obeys the law S equals half of gt squared. Where S is the distance in feet, and g is the gravitational constant. And assuming that we don't know this value, we wish to estimate it, and then at t squared, t is the time in seconds. Of course, theoretically speaking, what you can do is to do this experiment once and measure both s and t and plug in the formula and find g. That's it. And if you take a college algebra course, this is probably all you need to do. However, in this course, let me mention that if you just do this experiment once, your answer may not be accurate just because of the error in doing and conducting experiment. You don't want to make a mistake. You can be as careful as you can, but because you are a human being, your measurement will not be 100% accurate. So to make this more accurate, not 100% accurate, but more accurate, what we can do is to do this experiment several times. Every time we can choose a different s and different t squared. For example, this is the data obtained by somebody, and with s equals 1, so s is 1 foot, and the t squared value is 0.06. By the way, here we're using t squared because s is not a linear function of t. S is actually a quadratic function of t, and so we're going to use s versus the t squared. If you introduce another new variable, let's call it a big T called t squared, then s becomes a linear function of t. And then when s is 2, t squared equals 0.12, and etc. When s is 5, t squared equals 0.31. So if you plot all these points on the graph, and here is what you will get. And you can see there are 5 points. Those 5 points should be on a straight line, but they're not because of the reading errors. However, they are roughly on a straight line. So what we can do is to plot a straight line that's roughly fits the data. And also notice that our straight line passing through the origin, because when s is equal to 0, and when the distance is 0, and of course t is also 0, and therefore our line should have the y-intercept 0. So this is the line. And once we find this line and we can read a point from the line, find the slope, and have the equation of line t squared, where you plot as the vertical axis and as the horizontal axis, and t squared is equal to 0.02s and 0.06s. Now let's actually continue from here, and let's mention how we can find the gravitational constants from here. So recall from the previous slide, we're gonna have s equals half of gt squared. So this is where our starting point is. S equals half of gt squared. But now you have from this equation of the line, you're gonna have t squared equals 0.062s. So you can plug in this into this equation. So you get s equals half g times t squared, which is 0.062s. And now you cancel s from both sides. You get half g times 0.062 is equal to 1. So which means g times 0.031 is equal to 1. So g is the reciprocal, or sometimes called multiplicative inverse, of 0.031. And if you plug this into your calculator, you get a value that's approximately 32.2 feet per second squared. Of course, keep in mind that this is only an approximation. If you ask a different person to do this experiment, he or she might get a slightly different value, or even if the same person do it over time, you may get something slightly different. However, this is a more reliable way of calculating the value of t, and this is again approximation. And well, another thing you observe is that the points are mostly not on the line. The points are mostly not on the line. In fact, there is a difference between t squared and 0.06s, and that's the distance is what we call the residual. You see here, sometimes residual can be negative, sometimes can be positive, sometimes can be even be zero if you have a point that happens to be on the line. Notice that this third point has the residual whose absolute value is much larger than the rest of the data. And this is worth noticing because this usually means that point is less reliable. Is probably because you made a mistake or careless, something that's careless when measuring. So this usually is the result of some bad measurements. And so I would suggest you to do this point again. You would hopefully get a better result. All right, here is a reading assignment to make sure that you read example 10 from page 78 to 80 of our textbook. All right, let's just record the key ideas of this chapter. We introduce the equation of straight lines, and when do we know a function is relations linear? And then when you have a nonlinear exact relations, how do we transform it into linear relations by changing the variables? And we introduce black thread method for fitting data points. And also we introduce the idea of the residuals and how the residuals can aid us in identifying some bad measurement and things like that. All right, that's it for this video and also for the chapter. And thank you. I'll see you in the next chapter.